Hi there. Today, we want to answer the question of, do we really need to support that many syscalls in serverless VMs? So, let me give some background. The evolution of cloud computing has led to a shift towards microservices architecture, and microservices offer advantages such as modularity, language heterogeneity, and simplified debugging. However, they present challenges in terms of resource provisioning. The serverless or function as a service computing model has emerged to address these challenges. However, current serverless platforms suffer from virtualization overhead due to supporting unused syscalls. And current serverless platforms support a vast number of syscalls that user code or functions often do not require. This unnecessary support incurs significant virtualization overhead and leads to inefficient resource utilization. The research aims to design lean hypervisors aimed at reducing virtualization overhead by accurately characterizing user code requirements and optimizing resource allocation. The following sequence of events typically occurs in a provider's virtual machine. First, the serverless platform receives a request to execute a particular function from a client or event source. Then, the platform makes a remote procedure call or RPC to the VM or container instance, initiating the function execution process. This RPC call typically involves setting up the necessary execution context, including environment variables, function input parameters, or other metadata. Once the execution context is set up, the function's user code is executed within the VM or container instance. During this phase, the user code performs its intended logic, potentially making syscalls or system calls to interact with the underlying operating system or runtime environment. After the function's user code completes execution, another RPC call is made from the VM or container instance back to the serverless platform. This RPC call typically includes the function output, logs, or any other relevant metadata. Since we are primarily focused on the user code section, as it directly relates to the code in the serverless deployment, we employ a two-pronged approach to capture and utilize the entire process. First, we use Linux S-Trace utility to collect a comprehensive list of system calls made during the function's execution. This provides us with a detailed record of the interactions between the function's code and the underlying operating system. Simultaneously, we leverage the perf record tool to sample the call stack of the running function. This profiling data allows us to associate the system calls captured by the S-Trace with the specific portions of the function's code. By using the perf trace, we are able to generate flame graphs, which provide a visually intuitive representation of the function's behavior from invocation to completion. This approach enables us to achieve a fine-grained understanding of the interactions within the serverless provider's virtual machine during function execution. To ensure a comprehensive understanding, we conduct profiling on code implemented on 3 of the popular languages used in serverless functions: Go, Python, and Node.js. This allows us to identify language-specific patterns and challenges, as well as common trends across different programming paradigms. Importantly, our analysis excludes the network syscalls generated during the prologue and epilogue phases, as our focus is solely on the user code section. This table presents the functions we selected for profiling across the different languages, leveraging a diverse and representative set of common function benchmarks sourced from the vSwarm and vHive repositories. The analysis yielded valuable insights into their resource utilization and syscall behavior. Only 17 out of 303, or less than 6% of total Linux syscalls were required for the user code of the profiled functions. For example, the AES encryption function in Node.js required only memory management and synchronization syscalls, while the logistic regression serving function solely relied on event polling and synchronization calls. The payment service function, on the other hand, demonstrated the capability to execute without any system calls. This suggests that serverless hypervisors need to support only a limited subset of system calls to run the user code. Current serverless hypervisors unnecessarily support a vast number of system calls that functions do not require, leading to inefficient resource utilization. Only a limited subset of the full system call set is required across all functions analyzed. The opportunity exists to design a lean serverless hypervisor tailored to support only the necessary syscalls per function for the user code. This lean hypervisor can then be paired with another specialized networking hypervisor, increasing overall resource utilization. By doing this, we can adopt a targeted approach to resource allocation and improve the efficiency of serverless computing deployments. Thank you.